I mean, it's actually more in follow-up.
Yeah. This is the sign-in sheet for the grant. She needs to keep track of the attendance.
Okay, I believe everyone grabbed the food, so let's start. Yeah, so first, welcome everyone to come to the last HICE for this semester. And today, we are talking about the TW Hydrae and its Protoplanetary disk. It's after by the JWST NIRCam. Yeah, and we will talking about the motivation and some background, including some previous systems, and then show our results. Yeah, so let's start from introduction. What is the Protoplanetary disk? So you have adapters here inside the universe. Yeah, and if sometimes the string instability will cause the concave, and some dust will accumulate and form a central primary bands, and we can produce some protostar. And this stage take about 10 to 5 years to produce the embedded protostar. And then when time goes to millions of years, we start to format a Protoplanetary disk, which means that the disk will starting to align in a single plane instead of the spherical shape. Yeah, so it's happening around 1 million years to 10 million years. And then we are targeting a system that have a Protoplanetary disk. And we call the star in the center for the T Tauri star, yeah, for the Earth, for the sun-like star in early stage. Yeah, so the major difference between the Protoplanetary disk and debris disk is that in the debris disk, we mostly have the dust and platesimal and almost no gas inside the debris disk, and the scale height is more small. But for the Protoplanetary disk, we have a larger scale height and much more dust, much more gas. Yeah. So the TW Hya is our target. It's a young T Tauri star, and we believe its age is about 8 million years. And the distance is this here. And the reason why we're choosing.
Sorry, what is a T Tauri star?
Huh?
What is a T Tauri star?
T Tauri salt?
A T Tauri star.
Oh, it just mean it's the early stage of sunlight star. We call it T Tauri star.
Sorry, I completely missed that.
Yeah, it's here. So it's happening around. So you have the concave, and it will evolve into the embedded protostar. And after the embedding protostar, it will evolution to the Protoplanetary disk. And right now the star is still inside the disk, and it's really hard to derive images. But yeah, it's inside the dust, but we call it the T Tauri star.
Oh, okay.
Yeah.
I missed that part. I only noticed the first two ones on that image.
Yeah.
Young star is still pretty, basically.
Here. Sorry, I probably have to make the text larger, but yeah. Okay, but why we chose the TW Hydrae? And this is our result, one of our results. It's because first, it's really proximate to us, it's really close to us, so we can have high resolution on it. And second thing is that it has a wonderful orientation, so it's face on to us, and yeah, nearly face on. And in our research, we suggest the inclination is about 5 degrees. Yeah, and it's actually showing the analog to early solar star, just as I mentioned before. That's why we call it a T Tauri. And yeah, also it's a evidence of ongoing protoplanetary disk evolution and maybe the ongoing transformation. Though we didn't find that in this research, finding any evidence of planets. Yeah, but the gaps and ring may be produced by those protoplanets. Yeah.
Can I ask, so why is a near face-on inclination a more favorable orientation versus an edge-on inclination?
Yeah, it's because in this way we can see the structure in really clearly. If it's edge-on, we will see just a line instead of the 2D image. You can clearly see the structure. Yeah. Yeah, and here let's discussion about the previous research, and this image is taken by the HT Hubble Space Telescope, and they find this is paper in 2023. Yeah, they find there's a moving shadow here, and although it break down into 2 pieces. Yeah. So the shadow is moving counterclockwise, and actually that suggests that they may be produced by the much inner ring, in how to say the diff. So you can see there are several rings here, and that suggests maybe there's a much innermost ring have some inclination, not aligned with the outer ring. So they will produce some shadow in the outer ring, as you can see in the final image here. Yeah. And also, other than the visible light, we can take the image in the infrared on the right side, and this one is ALMA, is in the radio wavelength. Yes. And we can see there are 3 gaps here, and also 3 rings here. Yeah. That's all we see. And there's also, they suggest this spiral structure, and we also see this kind of structure in our image, but we result in different conclusion. Yeah.
So across all these instruments,
Yeah.
HSD, ALMA, sphere, they're all different wave bands.
Yeah.
So is all of this reflected light, or are we seeing like emission from?
Yeah.
I don't know how hot these disks are, or.
Yeah. So the disk is really hard. It's around 10. It could for the gas part, it could hurt us several thousand. Yeah. And so for this image is visible light, which is mostly the gas emissions. And if we go to the ALMA, it's obviously will the millimeter wavelength, so it will be showing the dust emission, and this one will be the scattering light for the near infrared.
Okay.
And also, yeah, visible light also the scattering. Yeah, from the gas, mostly in the gas.
So so with these protoplanetary disks at these different wavelengths, you're kind of probing different parts of the disk itself. So these are pretty optically thick, and so at the millimeter wavelengths, you're sort of expecting to be viewing more of the actual midplane of the disk itself. But because it's optically thick with all of the gas content, at the shorter wavelengths, you're looking more at like the flared part of it. So if you remember the figures that she was showing earlier about like the sort of flared structure of the disk, at those shorter wavelengths, you're looking more at sort of the top of that surface rather than the midplane.
And I think the point you're getting at, Yu-Chia, is that you're looking here at HST wavelengths at the small dust grains that are supported, that are lofted up into the higher planes of the disk from gas, right? But we are still seeing scattered light from the smaller dust particles. Yeah.
So this is scattered light. Here is scattered light. NIRCam, scattered light. Yeah. And then ALMA
Is the emission, yeah,
Yeah.
thermal emission.
is thermal.
And so let's go to our portraits. We are trying to detail the image the detail structure, and also try to figure out if there are any exophony we can find in these systems. And we tried two different methods to produce the final image, including the high pass filter, reference difference image, and the image deconvolution to further enhance the resolution for this FRDI image. So to do the RDI, we will need some reference star, and we are using, because the JWST the PSF is very stable, so we utilize all image between the November 1st, 2023 to April 2nd, 2025. And we observe in 4 different wavelengths. And the observation date is February 14th, 2024. And here is the results. So on the right side is a high pass RDI image, and then the left side is go through the deconvolution process. So this is 444. We can see there's a green here, and actually, if you cross look at here, you can see it's a bifurcation structure here, and also the different wavelength. And for the 201, this is the most clear one in our data set. You can clearly see there's a bifurcation structure here. Yeah, and then much shorter wavelengths, not so well for this image, but yeah, and we also try to do this inclination fitting. So we're doing this by trying to figure out the 4 parameters. So the x0, y0 means the center of the disk. So they are not necessarily the same position of the star position. So we just try to fix this, and also the inclination and position angle with fitting these 4 parameters, and the way is just try to find the minimized variance within the eclipse angle. And we're using the MCMC methods to do the fitting. And here is the results for 200 ones. And also, you can see the radial profile after fitting, before the fitting and after fitting. So this is as soon as a perfectly spaced on, and if we consider inclination, you could see a little bit improve in the deviation here. The arrow bar here is smaller right now after the fit in the inclination and position angle. Yeah. And also we do the similar thing for the 444, but probably because we don't have that. Not such good as the 201. We cannot show the inclination in 444. We just suggest the inclination is smaller than 5, and position angle still around 170. Yeah, and here is also showing the radial profile before and after the fitting. And yeah, so let's go to the conclusion. So in this observation and the data process, we can result in the disk is nearly face on with the inclination about 5 or 200 reference, and we couldn't find any exoplanet in this system. Yeah, and the third thing and final finding is the suggest a bifurcation feature in the outer disk. Yeah, and it's all for today.
As a question, so on the companion detection, you only showed images of the disk itself. I think also it'd be instructive to have a roll subtracted image so that to demonstrate that it's a very clean, no point sources detected kind of thing. That would.
Oh, I know how to. Yeah, we also do the ADI.
Yeah. So that would be a good, just for future.
Yeah, like the image, and then also the contrast curve measurement from that
Right,
increased
contrast
image.
curve. Yeah, perfect.
Yeah, so that would be pretty illustrative of, yes, you didn't detect any companions, and then the contrast curve.
And still constrain the primary we cannot find it.
Yeah.
Right. I mean, you use the contrast curve to sort of set an upper limit on the planets you could have detected. So that will take a little bit more work to sort of, convert those contrast curve measurements to a flux value, which you can then you can use planetary evolutionary models to sort of get an estimate of the largest mass planet you could have detected if you detected a planet in the system. So that's something that we can talk about, what the process is to figure that out. But
yeah, because within our sensitivity limits, we don't detect any planets, but that doesn't mean there could be a lower mass planet there that we just don't see. Yeah, for instance.
If I'm asked, what does the position angle mean for a disk? Because what is your 0 point, right? Because it's just. But like, if you have a star and a disk around it, right, and you rotate it, it's still a disk.
Right? Yeah. So it doesn't matter for the face-on disk.
Sorry?
I mean, there's no position angle for the face-on disk.
I mean, it's relative. So people kind of have different ways of doing it. My convention is to usually just measure an angle from north to the first disk ANSA you see. That's
So like the major axis.
the major axis.
Okay, I guess.
Yeah.
Okay.
Yeah.
So you're fitting an ellipse.
Yeah.
Okay.
Yeah, that's right.
Yeah.
Just fitting the ellipse, and we know if the dust density is constant, the brightness will go down with the R square.
Okay.
So it's different for different angles, and if we have the inclination, we can fit in with the eclipse. And
yes, it is more difficult to constrain for a face-on system.
Okay. Yeah, that makes sense. On a similar thing, for an inclination in your model, and as someone who doesn't do this at all, is it just the brightness that is the difference in like a circular disc that is very face on versus an elliptical disc that is tilted to the point where it looks face on? Is it just the relative brightness that changes, or is there something else?
It depends on the resolution you have. If you have a really high resolution, you can see the disk. And if you have a really low resolution, you can just see there's a data points. And you can do the spectrum, you can find the difference between the spectrum if the resolution is not high enough.
Yeah. Basically, you're just trying to figure out how circular your emission is. Is it very circular or is it more elliptical? And then from there, you just say, okay, well, if it's elliptical, then that's just taking a circle and inclining it.
Yeah, right. Like the general baseline assumption that we start with is that the disk is axisymmetric,
Mhm.
right?
That's right.
So a circle. And so, yeah, if you incline a circle, then it starts to look more like an ellipse, right? So, I mean, in some way, you can sort of estimate the inclination by, doing some calculations between like the size of the major axis and the size of the minor axis, because they have like a projection effect.
Yeah.
Any questions?
Maybe that was. Oh,
Like-
I do have a question. On when you do when you do your model fitting, you're using some sort of width for the
Width,
width for the annulus.
width,
Sorry.
the variation.
When you do the standard deviation
Yeah,
in the model,
yeah,
and you have some sort of annulus, right?
yeah,
And so what's the size of the width? What width?
3,
3.
yeah.
Okay, interesting. Okay, I was wondering if variations on that width might change your answer.
Actually, I also tried this morning with just the weighting by their pixel numbers.
Hmm.
We should do that,
Yeah, maybe like 5 or 6 or 7. So, see if
and also consider the brightness.
yeah.
Yeah, but it's really hard to build a noise model because we know the noise can come from several sources. Yeah, like if it's a photon itself, the photon noise is follow the Poisson distribution, but also the instrument or the ray noise, and also even the dust itself, they have some small structure.
Right. Yeah, because I was thinking that if you just assume it's a perfectly face-on system, but then you have intrinsic brightness distributions in the disk, what is, will the MCMC give something that it's because it's just trying to minimize standard deviation. So it might try to like fit a thing that's like, okay, well, I like it over here better than because it's a smaller, I think this is a better answer because it's smaller standard deviation in my model. So that was kind of the one of my concerns. So maybe changing. I'm trying to figure out a way of mitigating that uncertainty in the model fitting. And I don't know if there's a good answer to that, other than to inflate the uncertainties. I don't know. Yeah.
So I know we know what you're talking about, but I think maybe a lot of people in the room may not be familiar with the deconvolution process for your post-processing. So I was wondering maybe if you could explain what that is and why you do it.
Yeah. So the deconvolution is mean when this image we're using the telescope to do the observation, it actually not accurately get the same image. The point source will become it will be how to spread out by the instrument itself, and we call the spread out the PSF, the point, just the point spread function. And to get, so what we see is actually the true image goes through the PSF of the instrument, and we get the image in the final result. And what we're trying to do is just recover the original image from the final image we have, which called the deconvolution. Just consider the PSF instrument and try to figure out what the true image before goes through the instrument.
So the right is your actual image and your left is the deconvolved image.
Yeah. So
scale bars can be misleading because the one on the left is actually much brighter than the one on the right.
Because the central part is really bright and it will spread out by the PSF to the outside. So it's on the right side, it's not that bright as the left side, the left one.
One key thing here is this is a coronagraph, which has a changing PSF from this as it goes from the center outward. And so everything in the center is super suppressed by the coronagraph. And so the deconvolution method takes that into account. and brings back the original flux that was there.
What type of coronagraph is this?
It's not a hard stop. It's NIRCam's coronagraph is kind of it's the word I'm looking for, apodized.
Yeah.
No. It's like basically it's a Leo, but it has like it's an apodized shape. So like has a gradual, there's like all these dots.
Yeah,
like
I've seen that.
dots. Yeah. So it just has micro dots. So it's very dense in the center and then sort of sparse as you move outward.
So any question, Maroons?
Is your deconvolution, is it just like is it an iterative kind of method or is it more like?
Iterative.
Okay,
I think it's a Lucy Richardson method or some sort of variation.
it's not just like an inverse Fourier transform. Okay, yeah.
If only.
Yeah, especially for the chronograph, it's almost impossible.
Yeah, because every single position has a different PSF.
Yep.
And you have to take that into account using models. We use PSF models that tend to be fairly accurate.
Are deconvolution methods like flux conserving or?
Yeah.
It can be if you know your PSF. And in this case, we do.
So
But it's not flux, or it doesn't conserve this image flux. You know, if you total that one and total that one, they're going to be different because the PSF in the middle suppresses. And then the idea is that when you deconvolve it, it divides that out. And so you get back all the full flux that was in the center.
So if no more questions, thanks everyone for coming and enjoying the rest of food.
Thank you very much.
I guess based on the ALMA imaging,